Welcome back, everybody. Today we're starting a new unit. It's definitely going to connect to the unit of radicals that we just wrapped up. We will definitely be using those radicals within this chapter, but the unit that we're starting today is probably the most important, particularly if you're moving on to higher levels of algebra. It's the most important because the topics that we cover here just carry out through so many other things that you'll study in math. So I don't want to put too much pressure on you, but this is kind of a big one, okay? Now, we've talked about quadratic before and what that word means, but do you remember? What does it mean if an equation or a function or an expression is quadratic? So it is considered quadratic if it has a degree of 2. That means that you are looking at an x squared in your equation or your function or your expression. So that x squared, that degree of 2, makes it quadratic. Now, why is it important to know that it's quadratic or that it has a degree of 2? Well, it's going to tell us lots of things. In terms of equations, which is the focus for today, the degree is important because it tells us the number of possible solutions. And that's important, right? If we're solving an equation, we want to know how many solutions we're looking for. So in a quadratic equation, we are looking for 2 solutions. Now, before we look at some ways to solve, and actually 2 of the ways, one we've done for certain, which would totally be reviewed. The other, it was a real brief look, but hopefully it'll be familiar because it was not long ago. Before we talk about the ways to solve, I want to talk about the solutions. What are those 2 solutions that we're looking for? What are they going to look like? Okay? So I would argue that these first 4 equations that I put here, which all are quadratic equations, at least the first one and maybe the third, should be able to solve without me teaching you anything. Hopefully, maybe you have some thoughts percolating on that first one there. X squared equals 4. You can look at that and know what number you're squaring to make 4, right? Hopefully in your heads you're like, yeah, well, I could square 2 and get 4, so 2 is a solution. But remember, this is supposed to have 2 solutions. So that's one of them. What does the other have to be? Well, not only is a positive 2 squared going to make 4, but a negative 2 squared is going to make 4. So we get 2 and negative 2, okay? Now, when you're looking at the second equation, not so easy, right? Can we square a number and get 5? Can we square an exact, like a whole number and get 5? No. So what is the process that we could use to actually solve that? It's what we looked at, and I'm going to erase this and I'll show you why in a second. It's what we looked at when we were solving with our Pythagorean theorem. Let me go back for a second here. Remember we were solving like, I don't know, a squared plus 6 squared equals 10 squared. Well, we said that this would be 36, and then this would be 100, and we just subtract that 36 over. And then we're looking for what number squared makes 64, so we said 8, right? But technically, what were we doing? Well, to get rid of a square, what's the opposite of squaring something? It's taking the square root. So we took the square root, and we got x equals 8. Now, that poses a problem for us. Oh, let me go back here. That poses a problem here. If we just took the square root of both sides to solve, we would say the square root of 4 is 2, but we said 2 and negative 2 squared both make 4. Now, here's where you got to understand something important about square roots, okay? If I was alone, standalone, just saying what's the square root of 4, well, the square root of 4 is 2, right? And that's not going to change. That's what we call the principal square root of a number. But in this particular case, we're not really looking for the square root of 4. What we're really looking for is what number squared produces that 4. And since both a positive and a negative make that true, when we take the square root to solve an equation, anytime we square root, we have to put in a plus or minus in front of the result. So I'm not looking for the square root of 4. I'm looking for what squared makes 4. So when I square root to solve, we're going to put a plus or minus in, and then the square root of 4 gives us the 2. And we'll be able to get both solutions that way. And that's kind of how we would have to solve this one, right? There is nothing exact that we can square to get 5, but we can still solve this by taking the square root. So I square root both sides, square and square root cancel, so x comes down. Anytime I square root in the solving process, plus or minus, and then the square root of 5 doesn't simplify, so the square root of 5 is in our answer. So a positive square root of 5 squared and a negative square root of 5 squared are both going to produce 5. Okay? How about here? hopefully we know this one, right? But if we square rooted both sides, that's going to cancel. Technically, I should be putting in a plus or minus, but what's the square root of 0? Well, just 0. Is there a difference between a positive and a negative 0? No. So even though we're supposed to put plus or minus, it doesn't do anything here, which means just x equals 0 is our solution. Okay, now here's the really weird one. What can we square to make a negative 4? Again, hard to think about. So let's go ahead and take the square root. So x is going to equal, we're going to put in the plus or minus, and what are we saying for the square root of negative 4? Well, this can be simplified. We know the square root of 4 is 2, and if it's negative, it becomes imaginary. So we can have imaginary solutions to quadratic equations, okay? Specifically, these are how the solutions can occur with quadratics. If we look at the first two solutions, if I was to describe these two solutions are real numbers and they are rational numbers. So this would be two real and rational solutions. Now these two are still real. These two real solutions are still real, but they're irrational. Two real and irrational solutions. Okay, and the third one here, because the square root is 0, there's no distinguishing between a positive and a negative 0. We only got one solution, and it is rational. One rational, or one, we could say real and rational solution. And then this last one, we got two solutions, but they're not real solutions. That I going in there made them imaginary solutions. And then if you put the real with it, we could say they were complex. So this would be two complex, or if you just called them imaginary, I'd be okay with that, solutions, okay? And one of these four things is going to happen every time you solve a quadratic. So quadratic equations are either going to have two real solutions, like we had in the first two, or one real solution, like we had in the third guy there, or it's possible that there are two complex or imaginary solutions, okay? And one way to get those solutions is what we just looked at. It's saying, well, if we solve an equation, you know, we undo a plus with a minus, undo a multiply with a divide, we can undo a square with a square root. So the first way we're going to solve here is using what we call the square root method. It's trying to make the equations look like the first four here, where we just square root to undo the square. Now if we're going to use that process, these equations have to look like the first four, where that x squared thing has to be all by itself. So we're going to get the squared term alone. So in number 1, for example, this is my squared term. I want it to be all by itself, which means I'd have to add the 1, I'd have to divide the 2 before I could take the square root. Okay? So we're going to get that squared term by itself, and then we can get rid of the square by taking the square root of both sides. But we have to be really careful when we take the square root of both sides. So when I'm looking at this, right? When I'm looking at square root of 4, I'm not really taking the square root of 4 and saying it's a 2. I'm looking for what number squared produces that 4. So I have to remember to put a plus or minus in front of the number that we take the square root of, okay? So a plus or minus in front of that result. And then sometimes at that step you're going to be finished. Sometimes you may still need to continue to get x alone, and you'll see a few of those come up. But that's the gist, okay? So if I want to solve this using the square root method, I'm going to get that squared term by itself. So my first step is going to be to add the 1 to both sides, which is going to leave me 2x squared equal to 18. And now to get rid of times 2, I can divide both sides by 2. And that gives me x squared equal to 9. And now to get rid of the square, I take the square root. So x is going to equal, I took the square root to solve, so plus or minus, the square root of 9 would be 3. And so those are our two real rational solutions for that equation. And if you wanted to plug them in to check, you don't need to do this every time. But if you want to check your work, put in the 2, let's try positive 3 squared minus 1, and it should be equal to 17, and it is. And if you want to go in there and try the negative 3 squared times 2 minus 1, also 17. So if you want to check your work, you know, for the most part have some confidence that you're doing it correctly, but if you want to check, let's say it was a quiz, plug it in, okay? All right, let's try the next one. Again, I want to get this squared term all by itself. So the first thing I'm going to do here is get rid of this plus 2. I'm going to subtract it over, and that leaves me x squared divided by 5 equal to negative 5. And so how do I get rid of divide 5? Well, multiply by 5. Multiply by 5 on both sides, those will cancel. And now x squared is all by itself equal to 5 times negative 5 is negative 25. And now I can get rid of the square by taking the square root. So x is going to equal, I got to put the plus or minus in there. The square root of 25 is 5. Since it's negative, it's 5i. So those are our two imaginary solutions for that equation. Okay? Next one. I want to get the squared term by itself. So it's one step here. I want to divide both sides by 9. So that's going to give me x squared equal to, well, 49 doesn't divide by 9. That's okay. I can leave that fraction. And it's nice because they're both perfect squares. So in my next step, when I square root, the square and square root cancel. So x equals, got to put in my plus or minus. The square root of 49 is 7. The square root of 9 is 3. So it's plus or minus 7/3. Those are my two real and rational solutions. Okay, now if you look at number 4, it looks a little different. This time the term that's being squared is a binomial. That's okay. So I want to get that binomial by itself. So in this one, we're going to start by subtracting the 1 from both sides. So that leaves me this binomial, 2x minus 3 squared equal to 17 minus 1 is 16. Now I can get rid of the square, right? I can't move the 2 or the 3 because they're trapped in the parentheses. But I can get rid of the parentheses if I get rid of the square. So I'm going to do that by taking the square root. So that's going to give me 2x minus 3 equal to, don't forget, this is plus or minus 4. Okay, now I see a lot of mistakes happen on this particular problem. This is saying two things, okay? This is saying that, let me go to my scratch paper. This is saying that 2x minus 3 is equal to, when we say plus or minus 4, two things are happening here, right? 2x minus 3 can equal positive 4, or 2x minus 3 can equal a negative 4. And that should make sense. Let me go back here, right? If I square a positive 4 or a negative 4, I'm going to get 16. When I add 1 to that, I get the 17, okay? So when we're solving this, it might be helpful for you to break that into two different equations, where I add the 3 here to make 2x equals 7, and then divide the 2, so 7 has as a solution. And then I add the 3 here, so 2x is equal to negative 1, and then divide 2, so I get a negative 1/2. Okay? Now when I'm doing this, I don't like to do that much work. Now I think that makes it make a little more sense, but if you tend to be a little faster, maybe see this a little better. If I was solving this, I'm just going to do both things at once here. I'm going to add 3 to both sides, so 2x is going to equal. I got to recognize this is a positive 4 and 3, which makes 7, followed by a negative 4 and 3, which makes negative 1. And then from here, divide everything by 2, and then that makes my solutions 7/2 and negative 1/2. So to me, that is less work and more or easier for me to manage than splitting it out and doing the same work twice, just with a different result here. But if you're likely to make mistakes, this might be a better approach for you. Okay, you can choose. I'm going to show it the long way on the note sheet, but you can choose. All right. So here, again, this is saying that we can break this up here, that 2x minus 3 is going to equal positive 4, and that 2x minus 3 is going to equal a negative 4. So when I add 3 to both sides on this guy, add 3, then I'm looking at 2x equals 7, and then divide 2, so x equals 7/2 is a solution. And then over here, same steps, add 3, so I have 2x equal to negative 1, and then divide 2, so x is equal to a negative 1/2. So I have two real rational solutions on this guy as well. Okay? Oof, it's a lot. All right, that seems to be much harder than 1, 2, and 3. Let's try the parenthesis type again. So we have to get the squared term by itself, and this guy we start by adding the 2. That gives me x plus 1 squared equal to 24. And I can't move the 1, it's trapped by the parentheses. So I'm going to get rid of the parentheses by getting rid of the square. Let's take the square root of both sides. That gives me x plus 1 equal to plus or minus the 24. I can't square root, but I can simplify. So 24, this is bringing back our chapter 10, right, is 2 and 12, and that's 2 and 6, and that's 2 and 3, which means a 2 comes out and a 6 stays in. So radical 24 becomes 2 radical 6. Now, over on the last one here, I had a rational number, and I could add and subtract from that rational number and multiply or divide both results by 2. So I separated that out. But if you, oops, didn't ask for that. If you look here, if I want to subtract the 1, I'm not going to be able to do that and take the rational number here and combine with the irrational that I have here. So since those can't go together, I'm going to go ahead and just subtract, oops, let me go to green, just subtract the 1 from both sides and say x is going to equal a negative 1 plus or minus a 2 radical 6. Negative 1 plus 2 radical 6 and negative 1 minus 2 radical 6 are two irrational solutions. Since these can't be combined, there's no point in separating them out, right? We can leave our two solutions like that. Ugly, but they can look like that, okay? Just means there's some decimals. All right, there's one for you to try. If you're confident, give it a shot. If you want to just keep working along with me, here we go. Let's get the squared term by itself by dividing both sides by 3. So if that cancels, we are left with x minus 5 squared equals negative 9. I can't move the 5, it's trapped in the parentheses. So I need to get rid of the square by taking the square root. That's going to give me x minus 5 equal to, gotta put in my plus or minus, square root of 9 is 3, and because it's negative, it's imaginary. Now, just like the last one, I gotta get x by itself, right? There's still a minus 5 there, and I'm gonna go ahead and try to add it over, but I can't combine reals and imaginaries. They're gonna stay separate, so I'm gonna end up here with a 5 and then a plus or minus 3i. So get two complex solutions. 5 plus 3i is a solution, 5 minus 3i is another solution. Now, if you wrote plus or minus 3i and then plus 5, it's not wrong. Remember, the standard form for a complex number says put the real part first and then the imaginary. So it's a little more proper to leave it this way. So these are our two complex solutions for that equation. Okay? All right, so one way to solve a quadratic is by taking the square root. That is not the way we learned how to do it first. The first way we solved quadratics was by factoring. Right? Remember we were factoring, we did this in chapter 5, was the first time we did it again in chapter 6. So an equation like number 6, right? How come I can't just use the square root method on this one? So think about this. If I wanted to get the squared term by itself, I would subtract over the 13x, subtract over the 12. Could I just square root both sides and try to solve? Well, x would be alone here, but on the other side of the equation, I still have an x. Okay, I can't solve for x and have an x on the other side of the equation. So the square root method does not work on this type of quadratic equation. So what is the difference between this and the ones that we just looked at? Well, let me go back to, let's see, undo. Right, back to this. The reason this didn't work out was because of this guy, right? That x being on this side of the equation disqualified this as being a solution. So anytime we have an x to the first in the equation along with the x squared, we can't square root to solve. We can only square root if there's a squared term, and then everything else involved is a constant. So let's go back to these problems here, right? I got a squared term, and then a constant, that all things that can be combined, right? A squared term, constant, all things that can be combined. No x to the first tricking anything up, okay? So this square root method, maybe you want to make a note here, this can only be used when we have a squared term and a constant, no x to the first. So when the x to the first term is missing. So think about your standard form, right? ax squared plus bx plus c equals 0. If that's gone, if you have some squared term and some constant, then you're in good shape to just square root both sides, okay? Now if not, right, if that isn't the case, if you can't square it because you have an x squared and an x to the first in there, then you want to try to factor. So factoring means let's get this thing in standard form, make sure that it's in order and equal to 0, and then we factor. probably going to be bottoms up. And then solutions are the values of x that make each of those factors equal 0. Okay, so here, for example, 1 times 12 is 12. Factors of 12 that make 13 are 12 and 1. Dividing by 1, not going to change those. So this thing factors into an x plus 12 and an x plus 1. And so one solution is going to be a negative 12, and our second solution is going to be a negative 1. So two real rational solutions. Okay? Here, again, we want to make sure we're in order equal to 0. So we're going to start this one by subtracting the 4 from both sides. And then we're going to multiply. 5 times negative 4 makes negative 20. Factors that make negative 8 would be negative 10 and 2. This time we're dividing by 5. So we're going to reduce. And that means this factors into x minus 2 and 5x plus 2. And so we have one solution of 2 and another solution of negative 2/5. And remember, these solutions are the opposites of these reduced factors. So there's our two real rational solutions here. Here, we want to make sure we got a 0, so this like term is going to be combined here. We're looking at 15x squared minus 4x minus 3 equals 0. 15 times negative 3 is negative 45. We can use a negative 9, positive 5 to get the 4 in the middle. Dividing by 15, then reducing, we have negative 3/5 here, and then 1/3 here. So this factors into 5x minus 3 and 3x plus 1, which means one of our solutions is 3/5, and another solution is negative 1/3. And I realize I'm going really fast. Maybe you can slow-mo me or pause, okay? One for you to try if you want to give it a shot. Otherwise, let's put this thing in order. Multiply. Looking for factors of negative 60 to make positive 11. We can use 15 and negative 4. We're going to divide those by 10. Reduce. Reduce. So this becomes a 2x plus 3 and a 5x minus 2, which means negative 3 over 2 is a solution, and positive 2 over 5 is another solution. Okay, two real rational solutions. Now notice that all 4 of these had two real and rational solutions. If you have an equation that can be solved by factoring, that will be the case. Anytime you're solving by factoring, you're going to get two real rational solutions. Okay? All right, one more method. Why do we need another method? Actually, there are 2 more methods, but the 4th method is just so special it gets its own section of the book. But one more method for today, and let me try to show you why we need another method, okay? So let's look at number 9. Right now we have the square root method as an option, but I cannot square root here and square root here, like that's going to cause an issue. So square root method that we had as an option, not an option. The other option is factoring, but are there going to be factors of 1 that makes 6? No. So if it's not factorable, it's prime. That doesn't mean we can't solve this equation. It just means we can't solve by factoring, okay? Every quadratic equation is going to have solutions. It's possible that they end up being imaginary or irrational or ugly, right? But if we can't solve by factoring, there's got to be another way. So I'm going to show you another way that's called completing the square. What it means to complete the square is it means to take something like number 9 that isn't factorable and make it factorable. So it's the process that we use to take a quadratic function or equation that is not factorable, so that isn't factorable, and make it factorable. And we do this with a little witchcraft. Now, if I had a little more time, I would show you the whole background on it, but I think you're going to be more interested in the process. Standard form, like we saw with factoring, means put this in order and equal to 0, okay? When we're looking at our quadratic, if it isn't factorable, we're going to try to use this complete the square process. Now, to use this, our leading coefficient A has to equal 1. It's got to equal 1. And then this process is really nice also if B is even. Now, if those things aren't true, this process is still possible. We just have to work around those 2 issues, okay? Now, instead of, like when we're factoring, leaving our equation in standard form, what we want is the constant to be on the other side. So we want to move the constant. We're going to move the constant, so ax squared stays, bx stays, but c goes to the other side of the equation, okay? And then we're going to add a magic number to both sides of the equation, which is going to make one side factorable. And the magic number comes from a formula. The formula says to take half of b and square what you get. And that result is going to make the one side factorable. Now you have to make sure you add it to both sides. That's a legal move, right? Just like subtracting one from both sides to solve is legal, we can add anything we want to both sides and keep the equation balanced. So that is what we want to add. We want to add half of b squared to both sides. And that's going to allow us to factor what we have on the left, and it's going to allow us to simplify what we have on the right, and then we'll be able to solve using our square root method. Okay, so let me show you how this works. So can't square root, can't factor. Now you want to look for those options first because they're going to be easier than this one, but we're going to complete the square because those aren't options. So a has to be 1, and it is, so we're good. So we're going to get this equation equal to the constant. So x squared plus 6x is going to stay where they are, and so is the equal sign. I just want to move this to the other side. So if it's a positive 1 on this side, it's going to be a negative 1 over here, right? And then what I'm going to be doing is adding something to both sides of the equation. So what I like to do is put a little plus and a little blank on both sides, just so that I remember to add to both sides to keep the balance, okay? Whatever I add to one side, as long as I add it to the other, I'm not changing the equation. Now what we have to add is half of b squared. Now b is 6 in this one, okay? It's that middle coefficient. So b is 6, so I want to take half of 6, which is 3, and I want to square that. Now 3 squared makes 9. 9's my magic number. If I add 9 to both sides of the equation, look what happens. Okay, on this side, we can now factor. What are the factors of 9 that make 6? Well, they're 3 and 3. So I could write this side as x plus 3, x plus 3. But there's a more concise way to write that. If it's x plus 3 multiplied by itself, I can call it x plus 3 squared. And that's what's going to happen every time we use this process. Again, completing the square, it's making a binomial squared here, okay? So I have this binomial squared on this side. What do I have on the other side? On the other side, negative 1 and 9 makes 8. So I'm going to bring that down. And now what we can do is solve using our square root method, right? I couldn't factor this before, but then I was able to factor here, right? And now I can use my square root method. So completing the square allows us to actually put both of the other processes in play. So now I can square root both sides. So I end up with x plus 3 here equal to plus or minus. We're going to break down the 8. Let me change colors on that. We're going to break down the square root of 8. It's 2 times 4, which means a 2 can come out. So 2 radical 2. And then we're going to subtract the 3 to get x by itself. Subtract the 3 over. And x is going to equal, I can't really combine 3 and 2 radical 2, so the negative 3 and the plus or minus 2 radical 2 stay separate there. And there they are, 2 irrational solutions. Okay? Not the nicest process, but the more you do it, the easier it becomes. And if you don't like it at all, tomorrow I'm going to show you, well, not tomorrow, but Tuesday I'll show you another method that can replace this method. So I'm going to show it to you, but this is one that if you like it, you can use it. If not, you'll have a way out of this one, so don't freak out too much, okay? Now let's look at it again. This is a good candidate here. Can't factor, no factors of 6 and make negative 2. Can't square it because that x to the first is in there. So a is 1, we're in good shape. I want to move the constant, that's my first step. So x squared minus 2x are going to stay. The positive 6 is going to move to the other side as a negative 6. And then I'm going to be adding to both sides of the equation. Okay, now what am I going to add? I'm going to add half of b. b in this case is negative 2. Half of negative 2 is negative 1. And then I want to square that. So negative 1 squared makes a positive 1. Positive 1 gets added to both sides of the equation. And now on this side I can factor. What are the factors of 1 that make negative 2? Well, the factors of 1 that make negative 2 are negative 1 and negative 1. So I can factor this side into x minus 1, or x minus 1 squared. And on the other side, negative 6 and 1 makes a negative 5. Now I can solve using my square root method. Square root both sides. This leaves me an x minus 1 equal to a plus or minus. I can't break down the 5, but the negative is going to come out as an imaginary. And then to get x by itself, I'm going to add the 1. So this cancels, and I end up with 1 plus or minus I radical 5. Can't combine reals and imaginaries, so here it is, 2 complex solutions. Okay? One for you to try. If you want to give it a shot, feel free to pause. Otherwise, let's try this out here. So x squared, 8x gonna stay, gonna move the positive 10 over to the other side, so it becomes a negative 10. Gonna add something to both sides to make this work. So I'm adding half of b, which is 8, squared. So half of 8 is 4, 4 squared is 16. So 16 here, 16 here, okay? That makes this side factorable. Factors of 16 that make 8 are 4 and 4. So this side's gonna factor into an x plus 4, or x plus 4 squared. On the other side, 16 minus 10 leaves me 6. And now I can solve with my square root method. Square root both sides. That leaves me x plus 4 equal to plus or minus. Can't simplify radical 6. I'm going to move my 4 over. That cancels that. Can't subtract 4 from the radical 6, so negative 4 and plus or minus radical 6 stay separate. And there they are, my 2 irrational solutions. Okay? Now, I said in the beginning a has to be 1. If it isn't 1, then we want to make it 1. So what I'm going to do here to make this 1 is divide both sides of my equation by 4. So if I divide here by 4, I'm going to have 4 divided by 4 is 1 in front of my x squared. Negative 8 divided by 4 is negative 2 in front of x. And then I have this positive 5 fourths. And then on this side I still have my 0. So now I got a fraction in there. It's not ideal, but we can still go about our process here. So leaving the x squared and 2x, I'm going to move the positive 5 fourths over, so it's a negative 5 fourths. And now I got to figure out what to add to both sides of this equation. So I'm taking half of b, which is negative 2. Half of negative 2 is negative 1. I'm going to square that to get positive 1. So that's what I add here, and that's what I add here. And then factors of 1 that make negative 2, I feel like we just did this one, are negative 1, negative 1. So this is going to factor into x minus 1, or x minus 1 squared. And then on the other side, negative 5 fourths and 1. Feel free to use your calculator if you don't like fractions. Negative 5 fourths. And then if I add 1, it's going to be negative 1 fourth. So negative 1 fourth. And now I'm going to square root both sides. Square root, square root. X minus 1 comes down equal to plus or minus. The square root of 1 is 1, the square root of 4 is 2, and the negative makes it imaginary. Alright, and then my last step is to add 1. And so x is equal to positive 1 plus or minus 1/2 I. 2 complex solutions. Okay? Again, this process is easier in my opinion if a is already 1. You could imagine a situation where you have like, let's say it was 4x squared and then a 9x here and 5. Then you're introducing 2 fractions. And then over here you would go to take the half of the 9 fourths and get another fraction. And the more fractions that are created in this process, the uglier it gets. So if it's easy to make a 1 by just dividing and you still have whole numbers, by all means use the process, right? It will still work. But when dividing to make a 1 there, or when b isn't even, if it's really ugly, or if you just flat out don't like this process, I'm going to show you another way. So I think factoring, which we've done enough of, is pretty straightforward. I also like the square root method. But if you don't like completing the square, or